The definition of capacitance is that it's a ratio between charge and voltage. So if Q represents the amount of positive charge on the high potential plate of one of the conductors measured in coulombs, and delta V represents the potential difference between the two conductors measured in volts, then capacitance is a ratio of that amount of charge divided by the voltage measured in farads. And we're now familiar with this equation that we can write in triangle form. For example, if we want to know how to solve for the amount of capacitance, cover the C up with your hand, and we've got capacitance is equal to charge divided by voltage. So what's the capacitance on this parallel plate capacitor when it's uncharged, when Q equals 0? If Q equals 0, does that mean the capacitance is 0? Of course not. Whether this capacitor is charged or not, it has the same amount of capacitance. That capacitance is dependent on the spacing between the plates and the area of the plates according to this equation, which we derived starting with applying Gauss's law to determine what's the electric field in the region between the two plates, and then we used the definition for potential difference that says it's a line integral equal to negative E dot ds to figure out what's the potential difference between the top and the bottom plate, and then knowing that capacitance is defined as the charge divided by the potential difference, we derived this equation. Well, the parallel plate capacitor is not the only game in town. We could study spherical capacitors, or we might encounter cylindrical capacitors. In both those cases, we could use Gauss's law to determine what's the electric field in the space between the inner conductor and the outer conductor. Same thing for the spherical capacitor. What's the electric field in the space between the inner conductor and the outer conductor? If we know the electric field, then we can come up with an expression for the potential difference between the two conductors. And if we know the potential difference, we can apply the definition of capacitance that says it's charge divided by that potential difference. And so we're going to derive equations for the spherical and cylindrical capacitors. In this video lesson, we'll focus on deriving the capacitance for a spherical capacitor. So we'll say the inner solid sphere has a radius of A, and then to the inner wall of the outer conductor is a radius B. If we want to find the electric field in this space, we should make a Gaussian surface whose symmetry matches that of these charged conductors. So that would represent a good Gaussian surface. The total flux through that Gaussian surface is equal to the amount of charge inside that Gaussian surface divided by epsilon naught. And let's say we make the inner conductor connect to the high potential and the outer connect to a low potential of our source for potential difference. So here's our positive charge, and that leads to electric field lines that point radially outward. Okay, so if we choose any little patch of area of our Gaussian surface, the angle between dA and E is 0. So that allows us to get rid of the vector notation, and the electric field is just as strong in this region as it is this region as it is this region, so we can treat electric field as a constant and pull it out of the integral sign, and we're just left with E times, oh my goodness, what a horrible mistake I've made. I'm so used to writing E dot ds because of the definition for voltage as a line integral that I accidentally wrote Gauss's law as E dot ds, when of course I meant E dot dA. So we have E times the integral of dA is equal to Q in over epsilon naught, and the area of my Gaussian surface is 4 pi, not a, not b, but r squared. Now what's the amount of charge inside? Well, if this inner sphere is connected to the positive terminal, it's going to have some charge, capital Q. Of course, the outer conductor is going to have some charge, negative Q. So E equals 1 over 4 pi epsilon naught Q over r squared, which, by the way, is just the same thing as KQ over r squared. So no surprise there. Now what's the potential difference from point A to point B? Here's where I want to say E dot ds, right? The potential difference between the inner conductor and the outer conductor is negative the integral of E dot ds. We're probably just concerned with the magnitude of the potential difference in this case, right? So we'll say the magnitude of that potential difference is the integral of KQ over r squared dr as we go from A to B. The potential difference is equal to, well, you know, I'm not sure I want to write it as K. Let's go back to K is 1 over 4 pi epsilon naught. So anyway, delta V is 1 over 4 pi epsilon naught, better yet, Q over 4 pi epsilon naught times the integral of r to the negative 2 dr, which gives us negative 1 over r. Again, we're just interested in magnitude, so I'm not really going to pay attention to the negative sign. We're integrating from A to B. So we have delta V equals Q over 4 pi epsilon naught times 1 over A minus 1 over B. Well, I guess I really haven't ignored the negative sign. I switched the limits. Okay, now we can simplify this a little bit. Delta V is Q over 4 pi epsilon naught times the quantity B minus A over AB. And just found a common denominator, right? So what good is all this? Well, finally we can apply the definition. Capacitance is defined as charge per unit voltage. You know, we might as well start writing it like this when we do derivations of this type. Capacitance is equal to charge multiplied by the inverse of the voltage. So in other words, in this case, our capacitance would be equal to Q times the inverse of this expression, which would be 4 pi epsilon naught over Q times AB over B minus A. And the Q cancels out. So the capacitance for a spherical capacitor is 4 pi epsilon naught times the product of the radii divided by the difference in the radii. Contrast that with the equation for the parallel plate capacitor. This is capacitance is equal to epsilon naught times A over D. In our next video lesson, we'll see if we can apply the same sort of steps to figure out what's the equation that describes the capacitance for a cylindrical capacitor.